Hi everyone, this is Yiming. I'm a PhD student from HKUST, and it is my pleasure here to introduce our work, Camel Managing Data for Efficient Stream Learning. This work was done in collaboration with Professor Yan Yanshen and Professor Lei Chen. I will first introduce our background and motivation. So with the rapid increase of streaming data values, many real-world applications rely on machine learning models that are incrementally learned online. For instance, self-driving cars need to adapt to new environments. Robots equipped with multiple sensors learn to recognize new objects. Spam filters need to be incrementally updated. The problem here is how to efficiently and effectively update machine learning models over data streams. A very straightforward approach is to store all the data derived so far, and then retrain a new machine learning model with all the collected data at regular intervals. In this way, we can probably achieve good model accuracy. But since data volume keeps on increasing, it's impractical and computationally expensive to maintain all the data for model training. Another solution is using only the newly arrived data batch to continuously update model parameters. This figure shows a typical stream learning framework. So whenever a new streaming data batch BT arrives, a machine learning model should be updated on the fly without reviewing past training samples. Such a simple fine-tuning method also has its shortcomings. The first limitation is high training cost. Training models can be very large and complex. So fine-tuning such a model using new batches can be costly with respect to both time and resources. The problem becomes more severe when the new batches are in large volume. In that case, several data batches would accumulate in storage space, as shown in the figure on the right. The second limitation is low data effectiveness. In real applications, the newly arrived data may involve redundancy or many similar training samples, and directly using all of them may not improve model accuracy. For instance, consecutive frames extracted from videos are semantically similar. And the stream data set KDD 1990 is highly redundant, where over 75% of records are duplicated. On the other hand, the training model may have already acquired enough knowledge from previous training data. In other words, some newly arrived data points are straightforward instances which can be predicted easily. So it's unnecessary to use all the new batches since redundant data and straightforward cases will make little contribution to model performance. The typical stream learning framework would also suffer from the catastrophic forgetting problem. Since we're only allowed to rate data in one pass in the stream learning setting, model performance on past training data can degrade arbitrarily, especially when the stream data is not IID. To solve the above limitations, we propose a new framework, Camel, for the stream learning problem. Camel includes two parallelized data management components, concept selection and buffer update. To improve training efficiency for general classification tasks, Camel selects a concept from each streaming data batch for model training. Concepts are weighted summaries of large data sets. Since concept resolves redundancy in data and is much smaller, it would significantly speed up model training. Meanwhile, to alleviate catastrophic forgetting, Camel maintains a buffer of past representative samples as new data arrive. We repeatedly replace the sample to avoid forgetting past data distribution. Now we introduce how to do the concept selection for a stream learning problem. Here we first give the formal definition of concept. The input here of the concept selection problem include a data batch B, where xi is a feature vector and yi is the corresponding label, a parameter space big theta, and a loss function L. The output is a concept S represented by a weighted vector W. Wi larger than 0 means the data point xi, yi is selected in the subset, and wi equals to 0 otherwise. In this problem, we aim to minimize the approximation error LBW theta. It measures how well the selected coset set S can approximate the whole set B given model parameters theta. In general, cosets are model-oriented data summaries, such as a model optimized on the coset S can yield good performance as being optimized on the whole set B. We study the worst-case guarantee over the whole parameter space big theta, since it's impossible to predict what model parameters we can obtain on the training set B. The coset selection problem is known to be NP-hard for non-convex loss functions. This work satisfies the coset selection problem for general classification text over data streams. So each time a new batch BT arrives, we select coset for model training. In practice, the coset can lead to a linear speedup in model training if the data selection cost is negligible. Solving the coset selection problem is challenging. First, the coset is defined not only with respect to the whole set B, but also to the parameter space big theta. But in practice, it's computationally infeasible to enumerate the whole parameter space. Second, the coset selection problem itself should be fast. Otherwise, the cost saved from filter training data will be totally or even overconsumed by the data selection method. Finally, we need a solution with theoretic guarantee to ensure the quality of the selected cosets. To solve this problem, our key intuition is that if two data points are close in the feature space, then the corresponding loss values generated by model should also be similar. Then we ask this question, whether there exists a constant lambda, such that for any two data points, the differences between their loss values is bounded by this constant multiplied by their distance in the feature space. If so, we can efficiently bound the approximation error without actually calculating those loss values. In this work, we have proved that the constant lambda exists for common classification models, including regression models, DN, and CN, if the model's parameter space is bounded. We then develop an upper bound on the approximation error. So if the selected coset S is a dotted cover of the whole set B, and the loss function is lambda Lipschitz continuous, then we can bound the approximation error by lambda dotted. Since the term lambda on the right-hand side is constant, the problem becomes finding a coset S that can well cover the whole set B. So we can solve the coset selection problem by solving a variant of the facility location problem in the feature space. The dotted cover problem is NP-hard, but it can be transformed into a submodular optimization problem and efficiently solved by a greedy algorithm with approximation guarantees. To solve the catastrophic forgetting problem, Camel keeps a buffer of at most key samples over data streams and repeatedly replace these samples. A critical problem here is how to dynamically update the buffer. A simple idea is to update the buffer via residual sampling or ring buffer, but these algorithms assume that data streams follow an IID distribution, which doesn't hold in many real applications. Consequently, data patterns with a small probability mass in the distribution would be lost, while many redundant samples could be selected in the buffer. Both cases hurt model precision. In this work, we aim to maintain a buffer of representative samples that can best preserve the past data distribution. Our intuition is that coset satisfies some composition properties so that our coset method can be used to update buffer via a merge and reduce approach. To better illustrate our idea, we first define the epsilon coset here. We say that the set weight is an epsilon coset of the set P if the differences between their loss values is bounded by the parameter epsilon. For cosets with her merge and reduce properties, in general, the merge property says that the union of two bounded cosets is a bounded coset. And the reduced property says that The bounding cost set of a bounded cost set is also a bounding cost set. So we can update the buffer where merging the reduce. For each new batch BT, we first merge it with a buffer MT-1 to get a temporary buffer. So if the size of the temporary buffer exceeds the budget K, we run the cost set selection algorithm to reduce its size. Based on the composition properties, the approximation errors of samples in the buffer with respect to the data streams that have been observed so far is still bounded. Camel parallelize the data section and the model update stage to hide the data section cost. And in the abstract, the worker 1 is responsible for cost selection and buffer update, while the worker 2 only handles model training. If the data selection is always faster than model training, then from the perspective of worker 2, cost selection is as fast as random sampling. Then I will introduce our empirical evaluation. We separately evaluate our cost selection and buffer management algorithm. Specifically, we compare our cost selection algorithm with random sampling and full batch training without subsampling. We also compare our buffer management algorithm with random sampling and 6 total methods from the machine learning literature. This table shows the test accuracy of cost and random sampling varying the sample ratio on 10 datasets. It can be seen that cost clearly outperformed random sampling in terms of test accuracy in most cases, because our cost method selects representative samples from large data batch and avoids redundant computation on similar instances. It can lead to faster model conversions than random sampling. In contrast, random sampling often suffer from high variance and cannot satisfactorily resolve the redundancy in data. In this slide, the figure on the left suggests that the improvement ratio of cost set over baseline generally increase with data redundancy. Here, the improvement ratio lambda larger than 1 indicates that the cost set even outperforms full batch in test accuracy on some highly redundant datasets. Here, ImageNet is a particular case of little redundancy. It is because ImageNet has 1,000 classes, so that the number of training samples belonging to a specific class in a data batch is quite small. On the other hand, the cover type and core 50 datasets exhibit high redundancy due to low feature dimensionality and similar instances. Cost sets works pretty well on such redundant datasets. The figure on the right investigates the percentage of time saving and accuracy loss brought by cost set. Compared to training models without subsampling, cost set with a sample ratio R can roughly save 1 minus R of the total training time, which is a linear speedup. Although cost selection takes extra time, the cost can be hidden by parallelizing the data selection and the model training process. This is reasonable since training large neural networks is usually much slower than data selection. So overall, the results suggest that the cost can indeed improve training efficiency with a marginal accuracy loss. Here, this table demonstrates the superiority of our buffer management algorithm over the SOTA buffer replace methods on various data distribution. Specifically, we compare these methods on cluster incremental, domain incremental, and ID distributions. In general, our merge reduce and agglomerative clustering algorithm can outperform other baselines by a large margin in terms of test accuracy. As for runtime, our algorithms also are quite efficient among the compared methods. In summary, we developed a new framework for the stream learning problem. It includes 2 data management components, cost selection and buffer update. Our cost selection algorithm can achieve linear speedup in model training with a marginal accuracy loss. And we extend the cost selection algorithm to the stream setting where a merge and reduce approach, which can help maintain a buffer of past representative samples. And our experiments suggest that the effectiveness of cost set generally increase with data redundancy. Thank you for listening.